All right, let's take a look at a geometric object. Here I've got a very simple little triangle in the plane, ABC, and I want us to graph the dilation of this shape with a scale factor of 2. So let's graph what we get if we were to consider a dilation of this with a scale factor of 2. What does that mean? It means that every single coordinate, so A, which is 0, 3, B, which is 2, 4, and C, which is 5, 0, would then get multiplied by 2. And so what would we see here? Well, we can do this pretty fast. This is going to be 0, 6. This is going to be 4, 8. And this is going to be 10, 0. And so we can now plot those points, which I'm going to elect to do in orange. So A, the image of A is going to be A prime. It's 0, 6. It's up here. B is going to be 4, 8, 4, 8. So I put that up here. That's B prime. And then C prime is 10, 0. If we connect them with a straight edge, what we see is a very large triangle, and that is the image of this red triangle after a dilation by a scale factor of 2. Okay, great. So that's progress. But what I want us now to do is take a look at the various lengths of the triangle of the red and the triangle of the orange and compare them and see that, in fact, these triangles are, in fact, similar. We know they should be because we just took one and used a scale factor to get the other. So let's compute some distances really, really fast. You can use the distance formula, Pythagorean theorem, whatever you want. We'll do this pretty quickly. Let's take a look. So A, B. We want the distance between A and B. So what's the changes in the x's? Well, here with B, we're at x equals 2. And A is 0. And now we look at the y distances. The y distance here, B is 4, and y is 3. And so I see 2 squared, which is 4. 4 minus 3 is 1, so 1 squared is 1. So I see 4 plus 1 is 5, so I have the square root of 5. Now you have to do that now for each of the lengths. So BC, I filled that in already. And if you work this out, we see square root of 25, which is 5. And then AC, we do the same thing with that length. And when we do that, we see the square root of 34, which equals the square root of 34. Now let's turn to the orange triangle. How about A prime, B prime? Well, A prime, B prime, when you put in its coordinates, we end up with 2 square root of 5. When we look at B prime, C prime, we end up with 10. And A prime, C prime, we end up with 2 square root of 34. Now, this is so cool, because look at this for a second. This is amazing. Look at the corresponding lengths. Here's AB, A prime, B prime, and notice that the ratio of this to that is 2. Now look at BC and B prime, C prime. The ratio of 10 over 5 is 2. And finally, AC and A prime, C prime, if I take 2 square root of 34 and divide by square root of 34, I get 2. So this ratio is 2, 2, 2. We can see that, in fact, we have this great proportionality holding. And so we have actually seen that for real. I can write it down again for the biggest time. So we see that we've got 2 square root of 5 for A prime, B prime, versus AB, which is square root of 5, and that's 2. And then B prime, C prime equals 10. But what about BC? That equals 5. So we get 2 again. And you see it. A prime, C prime, 2 square root 34 divided by AC, which is just square root 34, and you get 2, 2, 2. And so what do we conclude? We conclude by side, side, side similarity that, in fact, these two triangles, this one which was generated from a dilation of the original one by a particular scale factor, in fact, are similar. No surprise, because if you take an object and dilate it, by any scale factor that's not 0, then in fact the answer you get will be similar. And we've just verified that for ourselves for this very special red triangle that we exploded up by dilating by a factor of 2 to get the orange. Anyway, have fun dilating things. It's really neat to take something, make it really big, and yet it's still similar to the original object. Very cool. I'll see you soon.